we can follow our starting points practically back to 13. Actually, we're not getting into the legitimacy of these speculations today for the most part, since the galactic local area has presently promptly acknowledged that our set of experiences in this universe begins with the huge explosion. Also, the thoughts that succeeded the Large Bang are additionally founded on a similar normal mark of the universe's introduction to the world. Unless you're a geek who has gone through hours observing several incredible perceptions of the huge explosion, to be fair, the peculiarity was in excess of a blast. So, the talk basically put the huge explosion found its starting point in a solitary point, a point that was endlessly hot and thick and expanded to outrageous lengths. All of this happened when the universe was amazingly youthful. In all honesty, at the hour of the enormous detonation, the universe was simply t to the power of less 34 seconds old, which is 100th of a billionth of a trillionth of a second in age. This is the point at which the universe encountered an amazing explosion of development, otherwise called the scandalous blast or the expansion. During this process, space extended quicker than the speed of light. Our universe was loaded with each molecule we found out about in our science class. Protons, neutrons, electrons, anti-electrons, photons, and neutrinos. The tradition of the huge explosion is supernatural. Well, metaphorically it seems as though it, however, how we might interpret the universe's initiation is exceptionally hypothetical. We've shown up lengthy ways starting from the main moon landing, and since then our innovative headway has developed dramatically. Back when researchers were concentrating on the huge explosion just in light of numerical recipes and logical models, they could not have possibly envisioned that we'd investigate the chance of life on Mars. There have been some large leaps forward in our interests to study the universe and investigate space, yet even then, our current innovation is pretty restricted. You see, we can't make the enormous banger peer back at the actual occasion. Our greatest piece of proof comes from the enormous microwave foundation that has permitted researchers to notice the reverberation of the huge explosion. While this instrument is momentous in the investigation of the universe, it's additionally hypothetically restricted. So while our whole information lays on the hypothetical occupants, logical hypotheses have a huge space to be invalidated. Also, that's right, we're almost sure about the enormous detonation and how it was amazing in making our universe. However, there are a few pieces of repercussions we've misunderstood. Furthermore, though surprising as it seems to be, hypotheses about our universe are generally founded on information that is inclined to human blunders all the time. Simultaneously, a portion of our information is additionally exceptionally decisive about the enormous bang. We should simply express that invalidating the theory is difficult altogether. The hypothesis, as our universe is yet expanding somewhat recently or something to that effect, our main redeeming quality in examining the huge explosion was the Hubble Space Telescope. Also presently, obviously, all wagers are on the phenomenal accuracy of the James Webb Space Telescope. Before we got to utilize these strong innovative instruments, one of the largest disputed matters in galactic review was the development of the UN universe. In the event that you get some significant sign, sense, or textbook from the mid-90s or so, you'd learn about how the universe is enlarging. All in all, the universe is extending, and that's one small scientific reality that we've clutched. Yet, the genuine disaster here is that perhaps we don't have the foggiest idea what the extension of the universe involves. All the more significantly, we must inquire ourselves in contemplating, assuming the universe is expanding because, fair warning, the James Webb Space Telescope is telling us. In any case, a modern-day miracle, the universe has quit expanding. Currently, prior to jumping into the implications of this earth-shattering movement from our universe's direction, we should just discuss our comprehension of this baffling peculiarity. In any case, deductively speaking, that kind of representation isn't right. Regardless of the boundless utilization of the blast and expansion of the word, the introduction of the universe wasn't precisely an impact. Also, researchers believe that we should address our comprehension of the universe. In NASA's own words, the universe didn't extend into space, as space didn't exist previously the universe. Rather, it is smarter to consider the enormous detonation as the simultaneous appearance of room everywhere in the universe. Our comprehension of the peculiarity reveals that our universe has lived through a sturdy grandiose period that was only disrupted by the association in space before the specific chemical gas. Our universe was just pitch black and dim when that was correct. As bunches of gas transformed into stars, cosmic systems really at that time did the universe rise out of its grandiose dark ages? So here's a little random information for you all. When do you think our nearby planet group came into being? Assuming the universe was just darkness and scariness for 400 million years. Well, our planetary system was born 9 billion years after the enormous detonation. What happens is that space has been expanding over time, and it carries matter with its direction. To place it in obvious words, the universe isn't expanding in the way we imagine it or even understand it. It is the dynamic expanding of space that precedes the expansion of the universe. We realize it's a bit convoluted to understand this, but on the other hand, it's significant to grasp the implications of what we are going to tell you for this video. We'd keep on using the expression expansion of the universe to imply the dynamic growth of our space, primarily because even scientists are comfortable using the specific framing to describe the recent discovery made by the James Webb Space Telescope. The fact that the universe has quit expanding is both startling and conflicting with our past theoretical knowledge on this confusing peculiarity. Since you see, with this stunning revelation, scientists were convinced that the universe was expanding at an accelerated rate since its origin. And well, they weren't amiss with the assistance of the Hubble Space Telescope. Researchers had the option to gather substantial evidence to support their theory. So, no, this isn't an instance of NASA revising its previous understanding of the universe's expansion. Whatever is happening to our universe is completely new and possibly irreversible. While the discovery itself is significant, it isn't too surprising either. As we discuss gravity, you'd see that our universe was dependably vulnerable to a collapse for the case when the universe had a more than adequate amount of energy density. The expansion would stop completely, and by the looks of it, our universe is moving in reverse. The concept of the universe's expansion has captivated human curiosity and scientific inquiry for centuries. It represents not just a physical phenomenon but also a fundamental aspect of our understanding of existence itself. From ancient philosophers pondering the nature of the cosmos to modern astronomers probing the depths of space with advanced technology, the expansion of the universe remains a central theme in cosmology. One of the pivotal moments in our exploration of the universe came with the realization that galaxies are moving away from each other. This discovery, often credited to Edwin Hubble in the early 20th century, provided the first observational evidence that the universe is not static but dynamic. Hubble's observations, using the newly built Hooker telescope at Mount Wilson Observatory, showed that galaxies farther away from us appear to be receding at faster speeds than those closer to us. This phenomenon, now known as Hubble's law, laid the groundwork for the Big Bang theory. The Big Bang theory posits that the universe began as a singularity, an infinitely small, dense point about 13.8 billion years ago. This singular point exploded, initiating rapid expansion and giving rise to the universe as we know it today. In the moments following the Big Bang, the universe underwent a period of extremely rapid expansion known as cosmic inflation. During this phase, the universe expanded exponentially, increasing in size by a factor so immense that it is difficult to comprehend. As the universe expanded and cooled, elementary particles formed and eventually coalesced into atoms. Over billions of years, these atoms clumped together under the force of gravity, forming stars, galaxies, and vast cosmic structures. The evolution of the universe from a hot, dense state to its current form is a testament to the interplay of fundamental forces and the remarkable consistency of physical laws across cosmic scales. One of the most intriguing aspects of cosmic expansion is its connection to the fabric of spacetime itself. According to Einstein's theory of general relativity, gravity is not just a force between objects but a curvature of spacetime caused by the presence of mass and energy. This curvature can influence the paths of objects, including light and other forms of radiation. In the context of cosmic expansion, the stretching of spacetime means that the distances between galaxies increase over time, even without the galaxies themselves moving relative to one another. In the early stages of our understanding, scientists believed that the expansion of the universe might slow down over time due to the gravitational attraction of matter. This idea suggested that the universe might eventually reach a point where it would stop expanding and start contracting, leading to a big crunch scenario. However, subsequent observations, particularly those made in the late 20th and early 21st centuries, have revealed a different story. In 1998, astronomers studying distant supernovae made a startling discovery. The expansion of the universe is not slowing down but accelerating. This unexpected finding, based on observations from the Hubble Space Telescope and other instruments, indicated that something other than gravity was pushing galaxies apart at an increasing rate. This mysterious force, dubbed dark energy, is now believed to constitute about 68% of the total energy density of the universe. Dark energy remains one of the greatest mysteries in modern cosmology. Unlike ordinary matter and dark matter, which interact through gravity and other known forces, dark energy appears to exert a repulsive force that counteracts gravity on cosmological scales. This repulsive effect is responsible for the accelerated expansion of the universe observed in recent decades. The nature of dark energy is still largely unknown. Some theories propose that it could be a property of empty space itself, often referred to as vacuum energy or the cosmological constant. According to these theories, even in the absence of matter and radiation, space-time has an inherent energy that drives the universe's expansion. Other hypotheses suggest that dark energy may vary over time or that it could be an indication of new physics beyond our current understanding. Understanding dark energy is crucial not only for comprehending the universe's past and present, but also for predicting its future. If dark energy continues to drive cosmic acceleration indefinitely, the fate of the universe could be drastically different from previous predictions. Instead of a big crunch or a cold, empty universe, the accelerated expansion might lead to a big freeze scenario, where galaxies drift farther and farther apart until they become isolated islands in an ever-expanding void. The implications of dark energy extend beyond theoretical physics and into the realm of observational astronomy. Advanced telescopes and space missions, such as the James Webb Space Telescope and the European Space Agency's Euclid mission, are designed to study dark energy and its effects on the universe. These instruments use sophisticated techniques to map the distribution of galaxies, measure their distances, and track the expansion rate of the universe with unprecedented precision. In addition to dark energy, the study of cosmic expansion has also shed light on the nature of dark matter. Dark matter, which makes up about 27% of the universe's energy density, is distinct from ordinary matter in that it does not emit, absorb, or reflect light. Its presence is inferred from its gravitational effects on visible matter, such as stars and galaxies. The discovery of dark matter was prompted by observations of the rotational velocities of galaxies and the gravitational lensing of distant light sources. These phenomena cannot be explained by the gravitational influence of visible matter alone, suggesting the existence of a vast, invisible component that interacts only through gravity. While the precise nature of dark matter particles remains unknown, their gravitational effects provide crucial clues about the structure and evolution of galaxies and larger cosmic structures. Cosmic expansion is also intimately linked to the formation and evolution of galaxies. Galaxies are not evenly distributed throughout the universe but instead clump together in vast clusters and superclusters. The gravitational pull of these cosmic structures influences the motion of galaxies within them and plays a crucial role in shaping their morphology and distribution. The study of galaxy formation and evolution has benefited greatly from advances in observational astronomy and computer simulations. High-resolution imaging and spectroscopy have enabled astronomers to study galaxies in unprecedented detail, revealing their internal dynamics, star formation histories, and interactions with neighboring galaxies. Computer simulations, based on theoretical models of cosmological evolution, allow scientists to recreate the formation of cosmic structures from the primordial fluctuations left over from the Big Bang. These simulations can simulate the growth of dark matter halos, the assembly of galaxies within them, and the interactions between galaxies over billions of years. One of the most intriguing aspects of cosmic expansion is its implications for the ultimate fate of the universe. While the discovery of dark energy suggests that the universe's expansion may continue indefinitely, theoretical cosmology still considers several possible scenarios for its long-term evolution. In addition to the Big Freeze scenario, where the universe expands endlessly, other theories propose different outcomes. The Big Rip scenario posits that dark energy could become more dominant over time, causing the universe to expand so rapidly that it tears apart galaxies, stars, and eventually even atoms themselves. This catastrophic scenario would result in the universe becoming a cold, featureless expanse of energy. Alternatively, the Big Crunch scenario remains a theoretical possibility, depending on the amount of dark energy and the overall geometry of the universe. If dark energy were to diminish or if the universe's expansion were to slow down significantly, gravitational attraction could eventually overcome cosmic acceleration, leading to a contraction of the universe back towards a singularity. The search for answers to these fundamental questions continues to drive research in cosmology and astrophysics. New generations of telescopes, such as the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope, are poised to revolutionize our understanding of cosmic expansion and dark energy. These observatories will survey the sky with unprecedented sensitivity and resolution, providing astronomers with a wealth of data to test existing theories and explore new avenues of inquiry. At the same time, international collaborations and interdisciplinary efforts are essential for tackling the complex challenges posed by cosmic expansion. Scientists from diverse fields, including particle physics, theoretical physics, and observational astronomy, work together to develop comprehensive models of the universe's evolution and refine our understanding of its fundamental properties. In conclusion, the study of cosmic expansion represents a cornerstone of modern cosmology, revealing profound insights into the origins, evolution, and ultimate fate of the universe. From the initial discovery of the expanding universe to the identification of dark energy and dark matter, each milestone has deepened our understanding of the cosmos and raised new questions for future exploration. As technology advances and our observational capabilities improve, astronomers are poised to unravel more mysteries of the universe. Whether probing the nature of dark energy, mapping the distribution of galaxies, or simulating the formation of cosmic structures, scientists continue to push the boundaries of knowledge and explore the fundamental principles that govern the universe on the largest scales. Ultimately, the quest to understand cosmic expansion is not just a scientific endeavor but a journey to comprehend our place in the vastness of space and time. By studying the forces and phenomena that shape the universe, we gain insights into the nature of reality itself and glimpse the intricate tapestry of the cosmos unfolding before us.